Welcome back to ECE 441A, 541A. It's a cloudy, cooler morning. Maybe you're not yet up too much, but you definitely need to be up and ready to go the next week. We have a lot happening between now and next Friday. Next Friday is your exam, but before that you have homework number 4 that is due. That's due Monday on the 15th. Homework number 5 is due on Wednesday, and you might watch for additional material that gets posted to D2L. There's already been one additional lecture, and that concerns steady state air and system type. That essentially follows the last time that we met. I posted that yesterday. I created that yesterday. That gives you hopefully a little bit better insight into system type and steady state air and what that means. Homework number 5 is obviously in Unit 5, and we're starting that today. That material is the Routh-Hurwitz test, and we'll get to that today, and that's why I might give you a little bit more material between now and the next time we physically meet. So watch for that, and I may send out an email if that does happen so that you can, if you are trying to optimize your time, then it might give you the weekend or a little bit more time on the weekend to work on homework number 5 in addition to homework number 4. All of that, one reason is because we will not be meeting in class next Wednesday, the class period before the exam number 2, and I won't be around in office hours, so Wednesday is a day that you can take to finish homework 5 and get ready for exam number 2. Exam number 2 is a week from today, and there is practice material on D2L, and essentially in a bracketed way, in a short way, here's what you should expect in terms of concepts or topics for exam number 2. You should be able to understand and compute and utilize the state transition matrix. You should be able to work with sensitivity. You should be able to either determine performance specifications, or once you're given performance specifications, figure out what that corresponds to in the S-plane as far as acceptable locations for poles that would satisfy those performance specifications. You should be able to compute steady state air in many different ways or for different locations in your system, and you'll be able to, after today and maybe another lecture, figure out how to use the Routh-Hurwitz criterion to determine the stability of a system without having to explicitly factor or find the roots of the denominator polynomial. The Routh-Hurwitz criterion is a way to find how many poles or roots of this polynomial are located in the right half plane, how many are in the left half plane, and how many are on the imaginary axis, without having to factor or find the roots explicitly, just with working with the coefficients of the polynomial. Fridays are wild. So today, Friday, it's wet. Next Friday, you have the exam. The following Friday is engineer's breakfast, and we will not be meeting in class the week after exam number 2 that day. Not the whole week, but just the next Friday after the exam on Friday, the 26th. Then the following Monday, lab number 2 is due, but lab number 2 is going to be, that content or that material will be a part of exam number 2. And that one really is emphasizing performance specifications and S-plane poles, and how do you select parameters to achieve that. So here's what I want to do today, is quickly tell you what the process is for exam number 2. Then we will talk about a design question, meaning if I now have a free parameter in my system, think a parameter in your controller. If I have a gain k or a value k, how do I pick that to achieve stability or achieve performance that I want in my system? That's the first question, and that hopefully will motivate the Routh-Hurwitz stability criterion, which is really, it's separated into two pieces. Maybe it should be Hurwitz-Routh, but it rolls off nothing rolls out of my mouth very smoothly. But Routh-Hurwitz is a little easier for me to say, I guess, just because of history or because of usage. But it's a two-step process. First, we have a Hurwitz test. That's a necessary test for stability, but it's not sufficient. So if it fails the Hurwitz test, then you can say, oh, my roots, I have something in the right half plane. If it doesn't fail that test, you don't know much yet. So you have to go on and create the Routh array. And when you're creating this Routh array, it's a table of numbers based on the coefficients of a polynomial. But in constructing that, you're going to have three possible cases. And each of those cases gives you different scenarios or different situations relative to determining how many of these poles are in the right half plane, how many of these, or roots of a polynomial, how many roots are in the right half plane, how many are in the left half plane, and how many are on the imaginary axis. We'll try to go through some examples. That might be the additional material that I provide. I'm already planning that what we do today, we will ramp up a little bit after you've had a couple more sessions of Routh-Hurwitz and show how you can use the Routh-Hurwitz process with an adjustable parameter to guide you in the selection of that parameter. And that I'm planning to be lecture 5.3. If you're keeping track, this is lecture 5.1. I don't typically keep track until I go back to D2L and I see which lectures are where in the units. But this one is now going to help us. This video or lecture will help us with homework number 5 and exam number 2. Exam number 1, you had one sheet. Exam number 2, you have 2 sheets of notes. Maybe we have a little bit more information. Maybe you need a little bit more space. If not, you can bring one, but again, the size is the standard paper, and you can have the front and back covered with those 2 sheets. You need to bring, if you want it, a table of Laplace transforms. That's table 2.3. You might have to go back to exam 1 to find that on the website, but you should be able to then print that out, and so you'll have 3 pages of your own material with you during the exam. 2 for your own notes, front and back, and the Laplace transform table is the front. You might want a calculator, something to write with. What's not allowed is, I think, given. No textbook, no class notes. I wanted to say no classmates, so no neighbor, no computer, and no cell phone. Questions on exam number 2? All right, let's start then by looking at this particular question. Can you find a value or values or a range for an adjustable parameter k to produce a stable closed loop system? Here's the closed loop system. We have a system. And where's the pole of that system in the open loop? Do you see that now just by looking at the transfer function? Where's the pole of our system? This is now, typically this would be our G of S, and this would be our G sub C of S. But a lot of times I'll just group both of those together and call them G. Maybe you want me to do something a little different. I could bar that. I don't know if I'll be consistent with that. But now we have G bar being the product or the loop gain of G sub C, the controller, and the plant G. So in this particular system, I'm telling you it's unstable, so you should have an idea as to where the pole is. If we sketched in the S-plane what we have, now our plant, if we didn't do anything, if we didn't have this controller, if we didn't have feedback, what would that plant do if we hit it with an input, or if we initialized it at some initial condition? What would happen as a function of time with that plant, with G of S? Where is its pole? At +1. So now if we went over here, we now have a pole in the right half plane. This is the plant. And what we're wanting to do is actually introduce a controller. And where is the controller's pole? It's at -2, and the idea is hopefully that combination, by adjusting the gain K, and if you've had a control class before, you can maybe envision the root locus. That's after exam number 2. We'll start with the root locus. That tells us how an adjustable parameter in your system can now move the closed loop poles from these open loop pole locations. What we're hoping is that by the appropriate choice of K in this controller, we're hoping that maybe what we can do is maybe we can locate those closed loop poles somewhere in the left half plane that will be stable or to our liking. They won't have to be at precisely those triangular locations, but maybe we can at least move that one that's unstable over into the left half plane and make it stable by the appropriate choice of K. So this might be our closed loop poles. And this is the controller pole. So if we're trying to design K to make our closed loop system stable, what are you thinking we need to do? Or what seems to make sense? This rain has us all cloudy, huh? What's the closed? If we want to stabilize the closed loop system, we probably need to examine the closed loop transfer function. And we have an adjustable parameter K that hopefully will enter into the closed loop denominator polynomial, and maybe we'll be able to adjust that to make our closed loop system stable. That's the idea. So the closed loop transfer function, in terms of G bar, with cheer 2, we have G bar over 1 plus G bar. And what's G bar? Well, that's the combination of our plant and controller in cascade or in series, and that's now K over S plus 2. There's our controller. And we also have the 1 over S minus 1 from our plant. If that's G bar and T is made up of some ratio of G bar, we can now compute T of S. Can I just write that down, or do I need to go through the steps? Well, let me go through the steps. So it's this, and then you can check my work. Now what's our strategy? Obtain a common denominator in the denominator. And then the denominators are common in the numerator and denominator. Those can cancel, and we're left then with k over s plus 2, s minus 1 plus k. That's what I was going to just write down, but I put in a step between there. So there's our closed loop transfer function, and it does have a k, the adjustable parameter, floating around in the denominator. And the denominator of that closed loop transfer function is going to influence or govern stability. So now we're interested in, can we find a value for k that would provide us with the two values of s, that when we set that denominator equal to 0, those two values of s will be in the left half plane. And if we multiplied all that out, we have s squared plus what? 2s minus s, or plus s, minus 2 plus k. And the notation that we will use is we will start labeling these coefficients. There's the a1 coefficient, and this is now the constant coefficient s sub 0. So that we now have s squared plus a1s plus a sub 0, and a sub 0 is adjustable by k. What we are going to learn is the following, and we're going to learn that once we've studied the Routh array. We haven't yet made it there, but this is a foreshadowing of where we're going. What we will learn is that a monic second order polynomial, which is what we have, i.e. we have this s squared plus a1s plus a sub 0. There's a monic second order polynomial. We're going to find that the roots of that are all in the left half plane, or that that polynomial is stable if and only if its two coefficients, which are a1 and a sub 0, as long as those two coefficients are present and positive. In other words, we want a1 to be bigger than 0, strictly bigger than 0, and we want a sub 0 strictly bigger than 0. If that's the case, then that particular second order monic polynomial will have its roots in the left half plane. That's what we will derive, hopefully today. We will prove using the Routh array that that condition is valid. So now, anytime, if you take nothing else away from today's class, I hope that you leave with the insight that, oh, if I have a second order polynomial and I want all the roots of that second order polynomial to be in the left half plane, I need a1 and a sub 0 to be present and positive. So I usually do a little bit of an upbeat dance because you're present and positive. You're not down, you're not negative. No, you're positive. You're present and positive. So if a sub 1 and a sub 0 are present and positive, then you have a stable polynomial. Is that clear? That's what you need to take away, at least, from today's class. So in our case, what does that mean? If we want a1 and a sub 0 to be present and positive, what do we need a1 to be? So in our example, what do we have? What's a sub 1? That's 1. So in our case, we need a sub 1, which is actually equal to 1, to be positive, and it is. That's a check. But what about a sub 0? A sub 0 is minus 2 plus k. To be stable, we need that expression to be positive. And we can now evaluate that for k. We can say, oh, k needs to be, we add 2 to both sides, and now we need, for that closed loop system that we've now designed with that controller, if k is bigger than 2, we will be stable. We will have both roots, both closed loop poles in the left half plane. So now we've done a design of a system. We've injected a controller. We've built a controller for an unstable system, and we've stabilized the system in the closed loop. We just need to pick a k, and we obviously need k to be bigger than 2, and it's probably needing to be bigger than 2. 2 is going to be right on the boundary of stability. Let's now figure out why we can make those remarks or state that fact about a sub 0 and a sub 1, and in more general, how can we decide whether our roots of a polynomial are all in the left half plane. So that's now bringing us to what I'm labeling as Routh-Hurwitz stability. If I have a system that's stable, what do I know is true about my system, or let's say the closed loop system? Where do I know the poles are? Bless you. Where are my poles if my system is stable? They're to the left, aren't they? They're in the left half plane. So now we have, and a lot of times instead of saying or texting left half plane, you can just text LHP. People will know what you're meaning. Oh, I'm in the LHP. Oh, you're in a stable state, maybe, is how you could interpret that. Whatever that means. All right. So what we want now with Routh-Hurwitz stability is we want a method for determining pole locations without having to factor the denominator polynomial, without having to factor d of s. If somebody gives us now a closed loop transfer function that has n of s over d of s, we've now identified the transfer function between our reference signal and the output, for example. The Routh-Hurwitz criterion is based on algebraic tests on the coefficients of that denominator polynomial. And who knows, my mood, hopefully it's positive. But even if it is positive, I might call that denominator polynomial d of s. I might call it delta of s. I might even call it q of s. Who knows? But you'll hopefully know by the context what I'm meaning by the denominator polynomial. So if that's the case, let's parameterize that or give that an expression or a formula. Suppose that the denominator polynomial delta of s or q of s is equal to a sub n s to the n. So we have an nth order polynomial, a sub n minus 1 s to the n minus 1. And that just keeps going all the way to a sub 1 s plus a sub 0. That's how we will denote or parameterize our polynomials. It's going to be nth order. So now if I have a 10th order polynomial, I'm going to have a sub 10 s to the 10. Here's the Hurwitz test. I said this Routh-Hurwitz is sort of a two-stage process, and the first step is to, if you're just looking for stability, you can perform the Hurwitz test first, and that might give you the information that you need. This is a simple test. To decide if the polynomial has roots in the right half plane. So I'm just going to say simple test to decide if the system is unstable. Here's the test. And I've already given it to you for a second order monic polynomial. The Hurwitz test is 1. We want all of the coefficients in that polynomial to be present. Bueller. So that's maybe too old of a... Anyway, all the coefficients have to be there. A sub 1, present. A sub 0, present. So if you do roll call on that polynomial, all of those coefficients have to be present. That's the first step. So that's pretty easy to check. The hard part is if somebody writes down the polynomial and they don't put in 0s. They just leave out the s and you go, oh, all the coefficients are there. You have to see, do I have some missing powers of s? If I do, then those are 0. They're not present. They're pulling a Bueller. So now all the coefficients need to be present and they all need to be positive. So all coefficients are positive. Those are pretty easy checks. Conditions. So these two conditions are necessary for stability, but they are not sufficient. Meaning, if this polynomial, if delta of s fails the Hurwitz test, then we know that our polynomial has at least one root in the right half plane. The system is unstable. However, if that polynomial delta of s passes the Hurwitz test, we still have a question mark. We don't know. We need more information. And on an exam, I probably won't just have you checking if a polynomial is unstable or stable. So even if it passes or fails the Hurwitz test, I might be asking you to do more. So we're going to get more information by building the Routh array or constructing this array. And so here is the procedure. Here's the Routh array procedure. First, we construct the Routh array. That's the first step. And we're not going to do that right now. Let's just say we're going to build it. So that's step one. Step two, while we are building that Routh array, we could confront three different possibilities. And I'm going to label those as A, B, and C. The first one is we get to build the whole array, and we look at the left column elements in that array, and we determine if all of those entries in that array are non-zero. So now we say that all left column entries let me say in the array, all left column entries in the array are non-zero. If that's the case, then we can look at all of those non-zero entries and we count the number of sign changes. If we have one sign change, then that's how many roots we have in the right half plane. If we had two sign changes, we would have two roots in the right half plane. So the number of sign changes really implies the number of roots of our polynomial, and I'm going to say with positive real parts. So those are belonging to the right half plane. Again, if you're texting this, RHP was sufficient probably for the generic population. Probably not. Okay. So let's look at an example of what I mean by sign changes of the left column entry. Suppose that the top row has an entry in the left column that's positive. The second row has an entry that's positive. The third row is negative. The fourth row is positive. So this is representing the signs of the left column elements. And now how many sign changes do I have in, if I just go from the top and look down, how many sign changes do I have? 2. So the hard part here is it's not the number of negative signs, it's how many times does the sign change. So from the first row to the second row, they're positive, no sign change. From the second row to the third row, it goes positive, negative. There's a sign change. But then from third row to fourth row, it goes negative to positive. There's another sign change. So this column would represent or correspond to 2 sign changes. And that tells me how many roots are in the right half plane. If I have 2 sign changes, how many roots are in the right half plane? Two. It's not rocket science on that particular case, right? All right, so that's case A. Case B, And that was when we constructed the Routh array and had all non-zero entries in the leftmost column. The second case is a left column entry or left column element in the array as we are building it is 0 with in fact non-zero elements elsewhere in that same row. An example of that, let's say that this is the s to the 5th row in our Routh array, and you build it and you have a 0 in the leftmost column, a 4 in the next column, and a 7, let's say 0.2 in the third column of that row. That's what I'm meaning by case B. I have a 0 element in the left column, and then I have some non-zero elements. I just need one non-zero element elsewhere in that row. So if I had 4, 0, that would still satisfy case B. What I do now is I replace that 0 with an epsilon. So in this case, I can't continue building my Routh array. I can't continue the construction without some value there in place of the 0, so I'm just going to let it be epsilon. So I replace the 0 element with an epsilon, and let me make that epsilon positive, and then I count the sign changes in the left column as this epsilon gets smaller or goes to 0. And as I let epsilon, so I might in subsequent rows have a left column that contains a left column entry that contains an expression involving epsilon. I let epsilon go to 0, and if that particular element has a negative sign as epsilon goes to 0, then it has a negative sign. I now count the sign changes in the left column, and again that tells me the number of roots with positive real parts, or the number of roots in the right half plane. That's case B. Case C is you're building up this Routh array and you end up with a row that's all 0. Then we have to do something else. Then we replace this all 0 row, I'm using some shorthand now, with the differentiated auxiliary equation. And I will typically call that auxiliary equation A of S, and I haven't even told you what that is, but that's coming. But once you replace that all 0 row with this new set of elements based on differentiating the auxiliary equation, then again you count the sign changes. And like before, the number of sign changes equals the number of roots with positive real parts. Here's the way we will find or identify the auxiliary equation. The auxiliary equation that I'm labeling A of S is created from the row immediately above the all zero row. So let's look at how we build. Let's do step number one. Let's build the Routh array. Here's the Routh array construction. And I don't know if everyone got the email earlier. Apparently my eraser didn't get the email, but in the email I asked you to wear your construction hats or your hard hats today because we would be building. All right, we're going to be doing the Routh array construction. Don't be looking for your email now. That's just going to distract you. There was no such email. So now we have the D of S is A sub n of S to the n plus A sub n minus 1 S to the n minus 1 plus A1S plus A sub 0. There's our generic formula or expression for our polynomial, nth order polynomial. Then what I like to do is actually for bookkeeping purposes, it's not necessary, but I actually like to tell myself what I have to play with. So I know I have an nth order polynomial. I'm going to just say, oh, here I'm going to label my rows. I have an S to the n row. I have an S to the n minus 1 row. I have an S to the n minus 2 row. And I just keep going. An S to the n minus 3 row, etc. And I just keep going until I end up with an S to the 0 row. But now I can populate the first two rows of my Routh array based on the polynomial that I'm given. And here's how I do it. S to the n, in the left entry, I put in A sub n. Then I skip over the next power in the polynomial and get this next coefficient. So I skip the A to the n minus 1 coefficient and I put in A to the n minus 2 in the second column of my array, in the first row. Then I skip over again, and I put in A to the n minus 4, A to the n minus 6, and I just keep going until I run out of coefficients. In the S to the n minus 1 row, I now pick up all of those coefficients that I left out in my top row. So now this one's left element is A sub n minus 1. Here is A n minus 3, A n minus 5, etc. until I run out of coefficients. That now is given to me once somebody hands me the polynomial. If it's fourth order, then I have an S to the fourth, and I should expect that many rows, S fourth down to S0 in my array. Once I've done that, now I start constructing the rest of the entries in this Routh array. Here's where we need our hard hats. So I'm going to have a B1, I'm going to have a B sub 2, and I'm going to have a B sub 3, and that's going to give me enough sort of information to show you what I'm doing. Then the next row is a C sub 1 and a C sub 2. Let me just quit there, but you could go on with those entries. Depending on, did I run out of columns to my right as I'm building up these values in the Routh array. So how do I build B1? Well, B1, or this B row, is built using the two rows above it. The C row is built using the two rows above the C row. and I focus a lot of my energy on the left column. I'm focusing a lot on that column, the leftmost column in that row. So now let me build up the B1 entry, and I've labeled it or colored it with blue. So now B sub 1 I need to build. And the way I build it is I take the leftmost column entries, 2 rows above, and I work with the column just to the right of the B1 element that I'm interested in. So now I'm working with this column to find B1, and I take a sub n minus 1 and I multiply it by a sub n minus 2. And I subtract from that a sub n times a sub n minus 3. That's B sub 1, and I divide it by a sub n minus 1. What did I just say? Who knows? I said a sub n minus 1 times a sub n minus 2 minus a sub n times a sub n minus 3 all over a sub n minus 1. That I built from the leftmost column and the column to my right of the B1 entry. To obtain B sub 2, it's a similar strategy. I'm still working with that column, but now I take a sub n minus 1 and I work with the column to the right of B sub 2. And I say a sub n minus 1 times a sub n minus 4 minus a sub n times a sub n minus 5. And divide that by a sub n minus 1. Once you know the strategy, it's not too hard. So I now have a sub n minus 1, a sub n minus 4 minus a sub n times a sub n minus 5 all over a sub n minus 1. So now can you tell me what B sub 3 is going to look like? B sub 3, I still work with the leftmost column, but now I work with the 2 rows above and 1 column to the right. So I now take a sub n minus 1 and multiply it by a sub n minus 6. I take a sub n, multiply it by a sub n minus 7 and subtract it, and divide by a sub n minus 1. How do I build the C's? C's, I use the 2 rows above and 1 column to the right. I'm always focusing on the leftmost column. So now I have B1 times a sub n minus 3 minus B2 times a sub n minus 1 divided by B sub 1. Let me write that down. And you can verify this or check this at home. B sub 1, a sub n minus 3 minus a sub n minus 1, B sub 2 over B sub 1. And C sub 2, again I'm working with the leftmost column, that's B1, but 1 column to the right, so that's now a sub n minus 5 minus a sub n minus 1, B sub 3 over B sub 1. And I just keep building up entries in my Routh array until I run out of coefficients. Let's now do that for our generic second order monic polynomial. now I'm saying here's delta of S. This is now S squared, it's monic, plus A1S plus A sub 0. Hurwitz test. Let's not even worry about that. You can fill that in later. That's true, right? We're assuming A1 and A sub 0 are present. We'll just assume that they're positive. To build the Routh array, how do we do it? How many? I start with S squared, S1, and then I end up with S0. And then I'm done. What's in the S2 row? 1, and then what's my next coefficient? I step over 1 power, and this is A sub 0. What's in the S1 row? A1. And nothing here. I leave it blank, so that will be a 0. Then I have my B1. And what's B1? B1 is A1 times A sub 0 minus 1 times this guy, which was 0, over A sub 1. And what happened? That became A sub 0. So when you have this blank, that A sub 0 actually pulls right down. So what are we going to do? Well, now we have a completed Routh array. We need all of the leftmost entries to be positive, to be stable. That means A1 is 0 or positive and A sub 0 is positive. I'll fill that in after class. But you can see that we've now validated that Hurwitz test is necessary and sufficient for a second order, and only a second order.